My name is Vinay Narayana. I run ML engineering at Levi Strauss and Company. I've been there for about a year. Prior to joining Levi's, I was at Wayfair, the online home furnishings company. I spent 4 years there doing their big data engineering as well as a ML engineering for about a year or so. Prior to that, I have extensive software development experience working at a company called EMC, which recently got, well, not really recent anymore. It's today called Dell Technologies. You probably know them. All right, today I'm going to talk about how we can create a cloud-native ML platform and some of the reference architectures that I want to go through with all of you. My deck is long and I only have 20 minutes, so I might skip a few slides as we go along, and I'll try to see if we can at least have a couple of minutes for questions. If not, I'm going to be outside. You can come by to ask questions. All right, so we're going to start off to level set everybody on what cloud-native architectures really mean, and then we'll talk about what the ML lifecycle looks like, and we'll have I'll spend some time on the overall cloud-native ML platform reference architecture. We'll walk through the various phases in ML development, and whenever you're proposing some patterns, you also want to propose or at least share what is the anti-pattern, right? So you can avoid those. So we'll talk about that in a slide. And then we'll end with a summary. All right, firstly, what is cloud-native architecture? Cloud-native architectures is basically a software approach that allows us to build, deploy, and operate applications in a cloud computing environment, just like any other public cloud. These architectures are generally involve microservices and containers, immutable infrastructures, and serverless or fully managed services. If you don't know what immutable infrastructures are, these are infrastructures which are resistant to change, and these are super critical for a ML platform for it to be reliable and stable. And lastly, any public cloud offers elasticity as well as a pay-as-you-go capability. So this is the MLOps lifecycle, which many of you are probably aware. It starts with data. No data, there is no ML. So we start off with ingesting data from your data warehouses or from a messaging platform like Kafka or whatever you have within your org. We go through the entire data engineering process of validating, standardizing, and finally creating what I call a foundational data layer. FDL, or a foundation data layer, is the foundational data that could be leveraged by consumers both in data science or analytics. In our case, we are focused on ML. So this is going to be more of extracting the data from the FDL and creating a highly curated feature data, hopefully in a dedicated feature store. And once you have your features in hand, obviously the next step is developing your models. As you can imagine, developing models and features go hand in hand. I show it here sequentially, but in reality, it goes back and forth. And once the model is developed and it works to your satisfaction, the accuracy is satisfied, we go to the deployment phase and we do the inferencing and all that after that. There's obviously monitoring that's needed at every stage, both from a model developed during the model development lifecycle, as well as feature monitoring, as well as data monitoring. So this is the reference architecture I was alluding to earlier. As you can see, the front and center of this entire architecture is a feature store. You want to use a feature store that is capable of serving your features both in an online mode as well as a batch mode. You want to leverage the same feature store for your training purposes. This is how you can avoid the skew that you generally find between training and serving. There is also a workflow orchestrator engine. It could be your favorite Airflow or Kubeflow or anything else that you use within your company. And there's also a continuous monitoring and alerting capability set both for your data as well as your model drift. And one of the salient features of this picture is really the SDK. And I have a whole slide to talk about what the benefits are of that SDK. So SDK, the reason this SDK is so critical, it abstracts away all the MLOps capabilities. If you really zoom out, what a data science or ML engineer does day in, day out, we are creating features, ingesting features, training models, and serving them either batch or online. All these are high-level tasks, and if you don't have one way of doing it, people keep repeating it in every data science team. The idea is to abstract away these common tasks in the form of a SDK. So that way, your teams will focus more on the creative aspects as opposed to repeating the same code over and over again. So I kind of already touched upon the second one. So you write code only once for each of these MLOps operations and then reuse it. Obviously, that helps us in accelerating your deployment into production. The company best practices, this is probably the most interesting one. Many companies, the companies that I've worked at, they have guidelines on how you can spin up your infrastructure resources. Let's say you're training a job and you need GPUs. Some companies might say, oh yeah, you know what, use as many GPUs as you want. But other companies might say, oh, it's going to be very expensive. You better get some permission before you do that. So you control, you put all these guardrails in the SDK so your users can only do what you want them to do. If they want to do more than the default support or default guidelines that are set by your infrastructure team, they need to get special permissions, right? So you can control some of that, or you can build some of those guardrails into the SDK. And the last one, future-proof. It's kind of an exaggeration a little bit, but hear me out. Many companies still out there are multi-cloud. And there are always conversations about either merging the clouds or moving from cloud A to cloud B. If you were to have a SDK that abstracts away your ML platform, just imagine the amount of effort it's going to take you as an ML team to update your code to support the new cloud that your company is proposing. It will be far less than actually going and updating every line of code for every model that you have running in production. Now let's dig into the various MLOps phases. These are the core tenets. For every of these MLOps phases, I'm going to talk through our core tenets. In this case, for data and feature engineering, the most important thing is you got to treat your data as a product. What does that mean? The person or the team that is generating the data should actually own the data until the point that it is consumed by your downstream user. Your downstream user typically happens to be a scientist or an analyst. So they own it end to end. There's a whole, big, I can talk for 20 minutes just on what data as a product means, but essentially at a high level, that is what it is. You also want to leverage a centralized feature store. For most organizations, most companies, one central feature store is sufficient, which allows feature discovery, which allows metadata store for keeping metadata about your features. But there is also something to say about some really, really large companies. I'm not talking about the big tech companies. I'm talking more like Procter and Gamble, those sort of companies. There are so many businesses under them. Maybe it makes sense for them to have multiple feature stores for each of their specific businesses. But for most of them, one central feature store should be sufficient. And last, you want to have continuous monitoring for both your data as well as feature. Now, this is, again, a high-level pattern, which is applicable for literally any cloud. You have your data that comes from your data warehouses. You have data coming from your source streams like Kafka or PubSub or Kinesis. And you also have data that flows from all the social media websites like Facebook or Instagram and whatnot. Your enterprise feature store should be a managed feature store. What I mean by that is you will have some foundational features or fundamental features that your company uses over and over again, pretty much in most of the models that you build. So one of those features could be something like an order ID if you're an e-commerce company. It's something that is used by almost all the data science teams in one format or the other. So in situations like that, you want to manage the quality of that feature within the feature store. So since if something goes wrong with this feature, multiple models will be impacted. And some of the ways to manage the features is this data validation framework that you want to build. There are a lot of tools out there. Some public clouds actually give you this capability out of the box. And there are also open source tools like Great Expectations and Soda that can do some of this work. So what I'm trying to get at here is when you are ingesting data, you gotta make your data go through this data validation framework. So you're basically validating the data as it streams or goes into the feature store. There are also situations with data where I've seen historical data changes over a period of time. And if your historical data is changing, obviously your model performance will also get impacted. So you also want to have a batch data validation job that runs at least once a day or maybe more frequently if you like, that is also validating the historical information. So with that, obviously you want to have continuous monitoring and alerting as well to detect any data drift. And lastly, from this feature store, you serve your models. And now let's get to model development. And some of the core tenets for model development include, again, leveraging cloud-native Jupyter notebooks. Most of the public clouds provide a pre-installed suite of your favorite ML framework. Could be PyTorch, Keras, or TensorFlow. And so all these frameworks come with pre-built containers as well, with the frameworks already, or sorry. I'm dealing with a little bit of cough. So this will enable, using these pre-built containers will enable us to speed up model development, as you can imagine. And most of these public clouds also enable you to run your training jobs in a distributed manner, and they give you the option to use GPUs or CPUs. And this is, again, a fantastic capability that I believe every science team should really look at leveraging. And last but not the least, AutoML. AutoML has been in the industry for quite some time. And when I talk to my data science friends, they're all pretty good at building custom models, and they can, if they spend enough time, they can build models that are better than AutoML models that are provided out of the box on any public cloud. The point I'm trying to make here is about still leveraging AutoML services to give you a baseline. So if you have a new use case that you want to build for your company, the business doesn't care if you're using AutoML or a custom model. So you do want to first look at what kind of performance you can get through these AutoML models and use that as a baseline. Maybe since it's a first iteration, it will be sufficient for your company to move into production with that. And you can challenge yourself to build a custom model that performs far better than AutoML. So this would be, in my opinion, very useful, again, in accelerating your productionization of models. This training pattern is pretty simple. You have Jupyter Notebook, you have the feature store. That is what you use for inputs into your model development. And then you have a training job, you have a model repository where you keep your model and all the various versions of the model. And then there's also a metadata store that keeps all the artifacts of your training. And these are also generally provided in the public cloud, mostly as a fully managed or serverless offerings. Next, looking at model deployment and workflow orchestration. And some of the core tenets of workflow orchestrations include scalability. They should have the ability to scale up or scale down based on the number of tasks that you're running as part of the workflow. It should be reliable. What it means is even in the event of a failure of your workflow, it should still be able to complete your task successfully. It needs to have the efficiency to run with least amount of resources and in a cost-optimal way. And last but not the least is extensibility part. It should be easily extensible to add new features or functionality. I'm going to skip this slide. Now, this is the CI/CD pipeline, and along with a scheduler. My experience is mostly in the Google Cloud. So some of the examples that I'm going to share over the next few slides are all in Google Cloud, but this is nothing to say it's not transferable to another public cloud. You have a GitHub. Everybody knows GitHub, then the CI/CD tool. In the CI/CD tool, this is where you run your tests. You compile your Kubeflow pipelines. In Google Cloud, Vertex AI is the ML platform. It is mostly serverless. You create your Kubeflow pipelines through the CI/CD pipeline, and then you schedule it to run. And this is an example of a Vertex AI training pipeline. So we had this situation in one of my previous jobs where our scientists were spending a lot of time using Airflow. Airflow was not cloud native back then. It's something that we managed in my previous company. They used to spend about 2 weeks' time to build capability to do hyperparameter tuning for their models. And they used to take at least 8 to 10 hyperparameters, and they train the models and then validate which model would perform the best. We built this quick capability inside Kubeflow or Vertex AI pipelines, and we got down that 2 weeks time that our scientists were spending down to less than 1 hour. And we made this generic enough so it was usable by multiple data science teams. For serving and inference, I'm just going to talk about the rightmost part of the slide. If you are serving your features in real time, let's say with ultra low latency, then you may want to deploy your model inside a Kubernetes environment. Hopefully with a local cache as well if it's needed. And these are some cloud anti-patterns. The first one probably is the most important one. Inefficient use of cloud resources or cost optimizations. That picture is quite a good representation of what happens in most organizations if you don't have close control on costs, especially if you're using serverless capabilities. It's easy for the scientists or engineers on the team to misuse the infrastructure, mostly unintentionally, and come up with a big bill for yourself. Inefficient queries is another major problem. People also tend to over-configure their containers with extra CPU, extra memory. So these are not cheap, especially CPU. In ML, in the ML world, continuous integration and continuous delivery are like ultra fundamental things. You really want to go beyond CI/CD to continuous training, continuous monitoring, and continuous alerting. And lastly, as you can imagine, in every cloud, most of the use cases can be done using more than one service. And if there's no control that you set on how those cloud resources or cloud services are used for which use case, you will soon have a sprawl of cloud services within your company. Again, you will have very little control on how people are executing use cases and the cost they are, or the charge they are causing the company. I'm going to skip this in the interest of time, and that's my contact information. Maybe we have 2 minutes left for any questions.